This animated diagram illustrates a microscopic cross-section of a standard magnesium strip. Before we can burn magnesium in a laboratory setting, we have to clean it. That's because the metal reacts with atmospheric oxygen over time, forming a stubborn outer layer of magnesium oxide. When we clear away that dull oxide layer, we expose pure magnesium atoms. If we apply heat, that solid magnesium reacts with oxygen gas in the air to form a fresh white powder, magnesium oxide. We write this physical process as a skeletal equation, Mg plus O2 yields MgO. But we have a mathematical problem. On the left side of our equation, we started with 2 atoms of oxygen. On the right side, we only have 1. The law of conservation of mass dictates that matter cannot be destroyed, meaning that second oxygen atom cannot simply vanish. Our equation is currently unbalanced. To fix this, we can scale the molecules up, but we can never break them apart. We add a 2 in front of the magnesium oxide product, which gives us our 2 oxygen atoms. That leaves us with 2 magnesium atoms on the right, so we place a 2 in front of our reactant magnesium on the left. The input now exactly matches the output, and that balances the scale. By tracking the atoms, we also reveal the nature of the reaction. Because 2 separate substances combine to form a single larger molecule, this is a combination reaction, fitting the structure A plus B yields AB. And because the magnesium achieved this through the gain of oxygen, it is specifically classified as an oxidation event. This animated diagram shows a more complex reaction. We start with solid zinc added to a solution of silver nitrate, which yields zinc nitrate and solid sulfur. When dealing with polyatomic ions like NO3, trying to count the individual nitrogen and oxygen atoms will slow you down. Since the nitrate ion stays intact on both sides of the equation, you treat it as a single unbreakable block. Notice that the zinc nitrate product requires 2 of those unbreakable NO3 blocks. To supply them, we place a coefficient of 2 in front of the silver nitrate reactant. Zinc is the more reactive metal here, so it displaces the silver from its partnership. We finish by placing a 2 in front of our isolated silver product to account for the silver atoms we just pushed out. Because one element forced out another based purely on its reactivity, this architectural shape is defined as a single displacement reaction. Let's test this logic. This diagram provides a word equation. Hydrogen gas combines with nitrogen gas to form ammonia, or NH3. Before you write out the skeletal equation, remember the rule for atmospheric gases. Hydrogen and nitrogen are both diatonic, meaning they exist in nature as paired molecules, not single atoms. Pause the video here to write and balance the equation. Let's check your work. Your skeletal equation should have started with N2 plus H2. To reach the balanced state, you need 2 molecules of ammonia on the right, which then requires 3 pairs of hydrogen on the left. This locks in a perfect ratio of 2 nitrogens and 6 hydrogens on both sides. Now look at this complex diagram featuring barium chloride reacting with aluminum sulfate. Notice that our sulfate ions are already pre-grouped into polyatomic bubbles to keep our count organized. Instead of a single element pushing another out, these 2 compounds perform a mutual exchange of ions. The barium pairs up with the sulfate, while the aluminum pairs with the chloride. That mutual exchange classifies this as a double displacement reaction. The barium sulfate it forms is an insoluble solid that settles out of the surrounding water. Because it forms that solid layer, this is also called a precipitation reaction, showing how the physical result maps perfectly to the chemical classification. This final diagram shows the exact chemical process of cellular respiration, keeping you alive right now. Glucose reacts with 6 oxygen molecules to yield 6 carbon dioxide molecules, 6 water molecules, and energy. Despite the sheer size of the glucose molecule, the laws of mass conservation remain constant. Every single atom is accounted for. The 6 carbons, 12 hydrogens, and 18 oxygens neatly unpack from the left side and distribute perfectly across the right side. Because this reaction releases energy outward into your body in the form of heat, it is an exothermic process. Furthermore, since oxygen is added to break the glucose down, this is an oxidation event. That places your own breathing in the exact same chemical category as a rusting iron nail or a rotting apple. This diagram acts as your master classification matrix. By stripping away the specific elements, we can see the 4 fundamental shapes of chemical behavior: combination, decomposition, displacement, and double displacement. By learning to lock your polyatomic ions together, track your diatomic gases, and map your atoms against these 4 structural shapes, you can balance the math and decode the behavior of any chemical reaction.